Can everybody hear me up there? Can you hear me? Okay. I'm going to pass around the attendance sheets, so sign your name. And last time we talked about sorting, lots of different sort methods, both general and specific for special cases where sorting can be done faster. We ended up with showing this competition between sorts based on random data, nearly sorted data, different kinds of data, and how they fare against each other. The n log n sorts tend to beat the quadratic sorts unless it's on really bad data for the n log n sorts, in which case the quadratic sort may actually beat them on smaller number of inputs. And today we're going to start talking about order statistics, which is kind of a subspecial case of sorting where you want to find not necessarily just total order on the numbers, but specific items like the largest, the smallest, the median, the ith largest, and other things. So if I say find the minimum about in a bunch of numbers, obviously it can be done in linear time, but it's not trivial completely because it's not obvious where the minimum is unless you do some work looking at all the items. So if I ask you what's the minimum of all these numbers, you know, it's not obvious when you first look at them. You have to actually do some work, and we'll get back to that. But finding the minimum problem is give you a bunch of numbers like in an array, and you find the minimum object or the minimum number. So obviously, well, maybe it's not so obvious, but that omega n, linear time, is necessary. It's also sufficient because you can quickly go through the numbers and find the minimum. But why is linear time also necessary? Well, you might say that each element has to be examined at least once. That's not quite a proof. It's an intuition. It's correct. But just saying that doesn't necessarily prove it. What you need to do is say a little bit more. So a more precise proof will say, assume towards contradiction that the minimum finding algorithm, whatever it may be, didn't look at one of the items and still gave out supposedly a correct answer. Well, that item that he didn't look at, call it x sub I, could have been minus a Google. And it would never have known that unless it looked at that x sub I, and x sub I is arbitrary. So if whatever answer it reported couldn't have been right in a general case, because something in that x sub I place could have been smaller than it, whatever it reported as the minimum, and so it couldn't have been correct in general. And that it refines the argument that everything must be looked at least once during the execution of any algorithm for finding the minimum. How many get that argument? Okay, it's pretty straightforward. It's a lower bound, and it's a lower bound not just on a specific algorithm for finding the minimum, but on any possible algorithm for finding the minimum. So it's a pretty easy lower bound. Lower bounds are generally hard to prove. In this case, we're lucky, and it's easy to prove this one because the problem is so simple. But in general, you'll see that it's not easy to prove at all because you need to prove a non-existence proof. Lower bound means no algorithm in the universe, either that we know of or that we don't know of, or that even some omniscient entity would one day could come up with. None of those will work faster than that time. So it has to cover a lot of ground. You have to prove you're not a millionaire, and it's hard to do in general. So it's a non-existence argument or proof. It's a form of proof by contradiction. So back to this. Still not clear where the minimum is unless I point it out to you. And there's minus a Google right there, which you may not have seen on the first pass until I pointed out that there it is. And if that one wasn't looked at, you would never have known the right answer. So you must, in general, look at everything. Okay. And often, a similar argument to what we just saw holds for many other problems, that every input data must be looked at. Of course, that gives you a linear lower bound. The linear lower bound is not that hard to come by, and it's not that tricky to prove usually. It's a similar argument to this one. The trick is to prove better lower bounds than linear, like n log n or even quadratic or whatever. Okay. And generally, there's not a lot of lower bounds known in computer science or in mathematics in general. The linear ones are relatively easy to prove, just like we did here. But that's not saying much. It means you got to look at the input before you purport to, know the right answer. But beyond that, it's hard to prove. We already showed a nonlinear lower bound for something else. Anybody remember what it was? What problem did we show a nonlinear, a superlinear lower bound for? Sorting, and that was n log n. And the higher the lower bound, the harder it is to prove in general. And very few lower bounds are known in all of computer science and math that are larger than n log n. For a few problems, there's quadratic lower bounds, but those are very few. And anything beyond that is extremely hard to prove because you got to cover so much ground that it's hard to do in general. Okay, so back to finding the minimum. So we showed a lower bound. Let's show an upper bound. An upper bound is just some algorithm that works, that meets that lower bound minimum. So very simple algorithm, just basically a loop and an if statement. If the item you're looking at is smaller than what you think is the minimum so far, then replace the minimum so far by that item and keep going. So it's like king of the hill principle. There's a current candidate for the minimum, and then you keep updating it if you see something lower than it. Okay, so the exact comparison count here is n minus 1 because you start with 2 in the loop and you keep going. So n minus 1 comparisons are sufficient. And this is not an asymptotic bound. This is an exact bound. Right? N minus 1 comparisons are sufficient. Why? Because this one does the job and it works every time. It's correct, this piece of code, this algorithm. And so this gives you a theta of n time algorithm because we already know the lower bound is linear. In fact, it's n. The upper bound, it's the same as the lower bound. So this algorithm here is asymptotically optimal. Now, what if you want to find the maximum instead of the minimum? Do we have to repeat this whole argument about the lower bound and then repeat some other piece of code, or is there some shortcut? Remember, sorting in ascending order and descending order was essentially identical. Why? You're going to flip the sign and then do the other thing, then flip them back, and then you'll have the answer. So same for minimum. If you want to find the maximum, flip the sign, find the minimum, get the result, and flip its sign, and you'll have the minimum. Right? If you want to find the maximum, you can find the minimum and use it to find the maximum. If you want to find the minimum, you can find the maximum and use it to find the minimum. So the two are equivalent, so we'll just worry about finding the minimum because finding the maximum is essentially equivalent. Okay. The trick is the question of whether we can do better than n minus 1. See, just because we had to look at all the data, it doesn't mean we had to do a linear number, n comparisons total. Just because we had to look at n data pieces didn't mean we had to do n actual comparisons. We could have maybe done less comparisons. So first we'll show that n over 2 comparisons are necessary. Okay. So comparing the total running time is different than comparing the total number of comparisons. They're not necessarily the same thing. They're related, and the running time is at least as large as the number of comparisons because you can't do more comparisons than you have time to do comparisons. But the thing is, if you say we must examine all the inputs, compare each input at least to something else, you have to understand that one comparison can compare two things. Two elements can be compared using a single comparison. So to touch all the inputs with some comparison or another, all you need to do is n over 2 comparisons, because if you compare the inputs in pairs, then you look at each one, technically, but you only exhaust n over 2 comparisons. So that doesn't show anything larger than a lower bound for a comparison than n over 2. How many understand that? So you got to do better than that if you want to show n minus 1 comparisons are necessary. Any questions so far? And now it gets more subtle. Okay. So just saying every input element must be looked at or compared to something else, that only gives you a lower bound of n over 2, not n, or not n minus 1. But it's not good enough. Okay. But it's still a non-existence proof for n over 2. So now we're going to refine this n over 2 lower bound to n minus 1. And this won't be as easy. Okay. So here's how we're going to do it. To find the minimum, we're going to keep track of the knowledge, quote unquote, the knowledge gained by doing comparisons, successive comparisons. Okay, so consider two broad classes of elements. First, all the n elements are in this unknown category. It's not a data structure, it's just a set of elements that are originally, before the algorithm starts, all the items are in this unknown category because we don't know if any of them is the minimum or the maximum or any other thing. They're unknown. And at the end, we'll know that almost all of them are not the minimum except one. Okay? So if you take two elements from the unknown category and compare them, you will know something about one or the other based on that comparison. And by the way, we're assuming all the elements are unique. Why is it safe to make that assumption? Why can we make the assumption that all the elements are unique without loss of generality? So every two items are either greater than, strictly greater than, or strictly less than one of the other, but they're never equal. What allows us to make this assumption of uniqueness without losing any generality about the entire discussion. Yeah.
If you have duplicates, then it doesn't affect the minimum.
Yeah, if you have duplicates, it doesn't affect. And even if you have duplicates, more generally, you can make them non-duplicates by breaking ties based on the index in the array where the duplicates came from. Just like in sorting. Right? Remember sorting? Just worried about unique elements, and it made it easier because you just have to worry about less than or greater than, but not the third case, and it makes the analysis easier and the algorithms easier. Okay, same thing here. So assume they're all unique. Okay, so the initial state is n things unknown and 0 things known to be the minimum or not the minimum. So this category here, in green, will be all the elements that have won against some other element in terms of comparison. They were greater than something else. They beat something else in terms of size, so they won the comparison. And if something won the comparison against something else, it can't be the minimum, so I'm denoting it also as min with a line crossing through it, saying it's not the minimum. So at the beginning, n elements are unknown, and 0 are known to be not the minimum. Okay, 0 are known to have won against something else, because we haven't done any comparisons. The algorithm didn't start running yet. Which algorithm didn't start running yet? I keep mentioning an algorithm here. Which one? Is it the algorithm from the previous slide? When I say an algorithm compares, is it this algorithm here? Remember, we're proving a lower bound on the problem of finding the minimum. So when I say an algorithm that starts with a state of n things being unknown and 0 things being known to be the minimum, which algorithm am I talking about now? It's not a trick question. It's a very simple question. We're proving a lower bound on the problem. Which algorithm are we referring to in this slide? Just to make sure you understand where we're going. One word. Which algorithm? Starts with an A. Want to buy another vowel? You could start with an E. I mean, it's not a unique word. Any algorithm. Why any algorithm? Why not some specific algorithm? Because I'm showing a lower bound on the problem. I'm not talking about the running time of any particular algorithm. I want to show how hard the problem is in general for any algorithm, any conceivable algorithm. Okay, how many understand that? Okay, so why didn't you say something here a minute ago? Okay, let's move on. So at the end, the final state of knowledge will be that one thing will remain unknown, and n minus 1 things will remain not the minimum, will already be known to be not the minimum. In other words, they would have won a comparison against something else. And so at the end, the state of the knowledge will be this, and this remaining one item in this category of item that didn't win against something else, that must have been the minimum of all the items. Again, because it's unique. There's only one item here that didn't win. All these items won against something, and because they won, they're not the minimum. This must be the minimum. So this is a representation of the state of any algorithm, the knowledge gained by any algorithm. I'm not saying anything about how the algorithm works or doesn't work, or what data structure it uses, or what language it's written in, or what computer it's running on, or which omniscient deity invented it, or anything like that. This applies to any of them, to all of them. Okay. So any algorithm needs to get us from this state to that state, and now we'll see the minimum number of steps necessary to get from here to here. So if you take two things from the unknown category, x and y, let's do it properly. So you take x and y and you compare them, and they compare like this. Let's say x is ending up being less than y. Again, because it's unique, we don't have to worry about the third case when they're equal. So x is less than y, and they're both unknown to begin with in terms of their minimumness, of the entire input set. What can you tell me about x and what can you tell me about y at this point? If x was less than y. Can y be the minimum? No. Can x be the minimum? It could. It doesn't have to be, but maybe it is, maybe it isn't. But y, for sure, we know it's not the minimum. So these two elements get reshuffled this way now after the comparison. X remains unknown because we don't know. We didn't win against anything yet. Y won against something, so for sure it can't be the minimum. And that comparison gained us this little bit of knowledge. Okay. And if you take two elements from this set, the green set, the ones that have already won, and you compare them, say y against z, and the comparison ends up being like this. What does that tell us about y and z with respect to the potential of being the minimum of either one of them? Nothing. But we could, in particular, because we already knew they're not the minimum, because both of them came from this green set, that they both have already won in previous comparison against something else. So we already knew that they're not the minimum. So comparing them to each other is not going to gain us any more knowledge than that, because we already for sure know that they're not the minimum. So in fact, we just wasted a comparison. Just because we did a comparison doesn't mean it's a useful comparison. Nothing stops you from doing a non-useful or not necessary comparison while you're running an algorithm. How many understand that? You can do it to your heart's content. You're just not making any progress. And that's okay. You can still do that. There's nothing. The universe will not implode on itself if you just keep repeating the same comparison over and over, and it's just not necessary. And here we're all about efficiency when it comes to algorithms. All right, so these two elements, after that comparison, still remain in that set. Neither one of them will ever migrate back to the blue set. No greens will ever migrate back to the blue. How many can see that? Because you already know something about it. Now, the other case is when you take a blue thing and compare it to a green thing, and it comes out like this. What do you know then? If this blue x compares less than this green z, what can you tell me about the blue x and the green z after the comparison? Which sets should they migrate back to after the comparison? Same. So the x, it's unknown. And if it's unknown, but it's less than z, it doesn't tell us it's the minimum. Maybe it's the minimum, maybe it isn't, so it's still unknown. The z, we already know it's in this set. It's not going to go back to the blue, so it's going to migrate backwards this way. So in fact, that was kind of a useless comparison too, if that's the way they compared, the x and the z. But what if the x and the z compare the other way? The x ends up being larger than the z. What can we know about the x now? Is it the minimum? Can it be the minimum? No, because it just beats something, so it can't be the minimum. The z can't be the minimum either, because that came from that set that already we knew not to be the minimum. So both migrate back to here, and we, again, made some progress to get us from this initial state to this final state. So basically, that's how the knowledge is tracked in the optimal most way. If you didn't waste any comparisons and you didn't make any blunders and recompare them when you didn't have to. Okay, so you notice that at each comparison, at most one element migrates from the blue set to the green set. And if you do unnecessary comparisons, that won't even be true. Not even one element, 0 elements will migrate, and you'll be spinning your wheels, not making any progress. And that's okay. The lower bound still holds, because to get from this state here of n unknowns to 1 unknown, right, it must take you a minimum of how many different comparisons at the very least? n minus 1. Because each comparison migrates at most one element, empties this unknown set by at most one element at a time, not two. So to empty it altogether from n to 1, you must make at least n minus 1 comparisons, no matter what the algorithm is. This logic here doesn't track an algorithm. It tracks the knowledge gained by any algorithm. The algorithm is non-specific. So this conclusion is general to any algorithm whatsoever. It's a lower bound on any possible algorithm for finding the min, and the lower bound is n minus 1 comparisons. Which means the algorithm we had on a previous slide, a couple of slides ago, that actually always terminated correctly with n minus 1 comparisons, is optimal. Now you know. It's not just optimal in the running time, which is linear. It's optimal in the actual exact number of comparisons, which is n minus 1, precisely. Not just any linear, not 5n, not 3n, not 2n, but n minus 1 precisely. That's a lower bound. And this algorithm now, we know, is optimal in two different ways. It's double optimal. It's optimal in the running time, which is big O of n. And it's optimal in the actual number of comparisons, n minus 1, precisely. And that's a good day when you can identify something as double optimal. Optimal in two things at the same time. I mean, it's rare enough to get an optimal in one thing or the other, but not necessarily in both. And notice that this lower bound, saying everything has to be compared at least once to something else, only gave us an n over 2 lower bound, not an n minus 1. The higher the lower bound, the better it is. The lower the upper bound, the better that is. How many get that? So you want to push upper bounds lower, and you want to push lower bounds higher. And when they meet, that's a very good day in algorithmic design. Okay? And we just had that experience very nicely with relatively little work. Usually it's a lot more work than this. And notice how much more complicated the proof of n minus 1 is than the n over 2. N over 2 was just a simple observation that every comparison must touch two things, and because n things must be touched, n over 2 comparisons must be necessary. That's it. That's this proof here. Short, simple. This proof here was not simple. This proof here was subtle and involved with looking at a bunch of different cases and examining the total knowledge gained by any algorithm, and this is hard to come by, this kind of proof. The previous proof you may have been able to finagle in a few minutes of scratching your head. This one, even days of scratching your head, you may not have this insight. Okay, but somebody did, and here it is. Oh, any questions about this? How many understand what's going on here? Okay. I only see half the class raising their hands, so ask me questions. Yeah.
So what did we exactly, because we didn't get the minimum in the last slide, right? For sure. We did n by 2 comparisons. We got local minimums n by 2, but we didn't get an absolute minimum.
Yeah. So he says we didn't get the absolute minimum. Think about it this way. This keeps track of the knowledge of any algorithm that uses comparisons to find the minimum, like the algorithm from 2 slides ago. And any other algorithm. There's many, many algorithms to find the minimum, not just that 2-liner from a couple of slides ago. That algorithm always finds a minimum. That algorithm is always correct. So at the end, that algorithm will find the minimum. In this slide, we track the number of comparisons absolutely necessary for that algorithm to do its job. And it could take more than that. But this is the very least. And any algorithm that finds the minimum starts with not knowing anything about any of the inputs because it didn't look at them yet. It didn't start running yet. And that's this state here. And things are unknown. And nothing has won against nothing else because no comparisons were executed yet by that algorithm. That could be any algorithm whatsoever. And at the end, that algorithm must know for sure that one thing is the minimum and all the other things are not the minimum. And how can an algorithm know that? By comparing things. So every time it compares something, we're charging it 1 unit of cost, a comparison. So as it keeps comparing things, we're observing that the number of unknown things about which the algorithm knows nothing can only diminish by at most 1 with every comparison. So the number of comparisons it needs to make is n minus 1. Is that okay?
Yeah, I agree with this. Like, I didn't understand what we were trying to prove on the last. We said like n by 2 comparisons were necessary.
Yeah. So here we said n minus 2 comparisons are necessary. And that's correct. But it turns out that in addition to that, n minus 1 are also necessary. So to buy a car, $1 is necessary, but it's not sufficient. You may need about 20,000 of those to buy the car. So 1 is a lower bound on the price of a car, $1. True statement. But $20,000 is a better lower bound on the price of a brand new, reasonable car. That's also a true statement and doesn't contradict the first. Okay, that's a good question. So I'm glad you asked it. Any other thoughts or questions? Okay. Now we can go deeper into this stuff. Now that you see how it goes. So n minus 1 are necessary, n minus 1 are sufficient, and that's why the algorithm from 2 slides ago is optimal. All right. What if you want to find the minimum and the maximum? Both. So come up with an algorithm that finds the minimum and the maximum, and then we'll show a lower bound for that, and an upper bound. The upper bound will be much easier. The lower bound will be even harder than what you just saw. What we just saw is a pale, version of what we're about to see. So we're building up to it. All right, so there's many ways to find the minimum and the maximum, just like there's infinite number of algorithms for any particular problem. And I just made a profound statement that may not be obvious. Why is there an infinite number of algorithms to solve any particular problem? There's an infinite number of codes or programs to solve any particular problem. And they're all different from one another. All these pieces of code are different. You can always add useless steps. Exactly. And the steps may not necessarily be all that useless. Some of them may contribute to the work, but not in a necessary way. How many understand that? It's subtle. It's not complicated. It's not complicated, but it is subtle. So to add two numbers together, there's not just millions of algorithms. There's an infinite number of algorithms to add two numbers together. Take the two numbers, play a lot of rounds of chess, and then spit out their sum. Well, that solves the addition problem. The chess part was not necessary. But nothing stops me from doing that, and the algorithm is still correct, still valid. It's just a lot less efficient than much quicker algorithms without playing the chess in the middle. Okay. I'm not being facetious. I'm just making a point that you need to understand. So there's lots of algorithms for everything, and when we show lower bounds, we got to cover them all. Just like when you try to prove you're not a millionaire, you got to cover all bases, including offshore accounts in the Cayman Islands, and including lottery tickets in your drawers that you haven't cashed yet, and that would make you a millionaire, and on and on and on. There's a lot of cases, an infinite number of possibilities. Okay, here's an obvious algorithm to find the min, but before that, if you want to find the max, you can just find the min of the negative of all the input. So finding the min and the max are the same. So to find the min and the max, what you can do is first find the min using the algorithm from before, and then find the max by finding the min of the negative of all these numbers using the algorithm from before. How many comparisons is that total? By doing it that way in two steps. Find the min and find the min of the negative, which is the max. Twice what was that before? So precisely in terms of n is what? 2n minus 2. Yeah. Okay. So obviously we're going to try to do better than that because that's too simple. Right? So n minus 1 to find the min, n minus 1 to find the max, total n minus 2n minus 2. And notice that you're doing it independently. You're finding the min and you're doing all these comparisons, and when you find the max, you're doing a whole bunch of other comparisons and completely ignoring the first set of comparisons that you already did that may get you a lot of information that you're now discarding and ignoring. How many see that? Because you're doing it independently. And that's a shame. And it turns out that's not efficient. So now we'll try to do better than 2n minus 2, and that's where things get more subtle. So here's the new algorithm that works better than that even, to find the min and the max. Here are the numbers in the array. These are the indices, array x1, x2, x3. And these are all different numbers. I'm just showing you the indices of the array. But I'm going to compare them in pairs. I'm going to compare the first two. And then one of them will be the minimum of those two, and one of them will be the maximum of those two. Just those two. So the comparison of the first and the second element gives us a min and a max of the first two elements. And I'm going to save both of those, not discard them. And I'm going to compare all the others in pairs. Find the minimum of the first, of the number 3 and 4, and then the other one will be the maximum of 3 and 4. Whichever the minimum is, the maximum is the other one. And I'm going to keep doing that. Find the min of all the pairs and the max of all the pairs. And how many comparisons does that take total to find all the mins of the pairs and the max of the adjacent pairs just like that? How many comparisons total? N over 2, right? Because I did them in pairs. Let's assume n is even. So that's n over 2 comparisons. Now, the max of the entire set of the original array X is located where? In blue, in green, or unknown, or where? Where is the total max of everything? What do you have to look at the very least? Or at best? Only the green. The max can only come from these green candidates up here, not from the blues. The minimum can come only from these blues and not from the greens, which are the maxes. How many get that? So now we have a lot less candidates for the total min and the total max of the entire original set. So we then made a big shortcut. Right, so now you just got to take the min of all these guys in blue, and then you got to take the max of all these greens, and that'll give you the min and the max of the entire set, and that another n over 2 comparisons, because it's only n over 2 maxes candidates and only n over 2 min candidates. So now you can employ the algorithm from 3 slides ago that finds just the min in a set straightforwardly. Find the min of all those. It's n over 2 minus 1 right there. And finding the max is also n over 2 minus 1 comparisons. And at this point, you know the answer overall. And the total number of comparisons is n over 2 minus 1 plus n over 2 plus another n over 2 minus 1, which is 3n over 2 minus 2. And so 3/2 n comparisons, or 3n over 2 minus 2 precisely, comparisons are now necessary. Are now sufficient to find the minimum and the maximum both. We're about to show that it's also necessary. That's the hard part, actually. So this is the easy part. The easy part is showing this algorithm. It's not obvious, but it's less obvious than the previous one. Find the min, then separately find the max. This does them together, and thereby you save. What percentage of the comparisons are saved by doing this more elaborate scheme than the previous scheme on the previous slide? How many comparisons did you take on the previous slide to do? This is a straightforward. Find first the min, separately then find the max, and there you go. How many comparisons was that, just for the record? That was 2n minus 2. This is 3/2 n minus 2. So the savings from 2 to 3.5 to 3/2, 2 to 1.5, that's what? 25% savings. That could be substantial. Right? If you have billions or trillions of things that you want to process. All right, any questions about this? This is an algorithm. This is not a lower bound. I'm not going to bother writing in pseudocode, but the scheme is pretty straightforward. Often we won't write the code or pseudocode, but hopefully if you understand the scheme, you can write the code pretty straightforwardly from that. If all you can do is code and don't know how to design algorithms, you're in trouble. And this class is not about coding. It's about algorithm design. These insights to get you to efficiency and optimization in some interesting and possibly clever ways. And if you had to, if you absolutely had to, you can sit down and write the code, sure. We're assuming you all know how to code. Any questions about this? Because next, we're going to show that 3n over 2 comparisons are not just sufficient, they're also necessary. They're also a lower bound. That won't be so easy to show. Which means this algorithm is optimal 2 different ways. Once we show the lower bound that 3n over 2 minus 2 are also sufficient, not just necessary, we show they're both sufficient and necessary, then this algorithm, which gives you 3/2 n minus 2 comparisons, and that makes it sufficient, because it's also necessary. This algorithm is optimal 2 different ways. It's optimal in terms of running time, this is obviously linear running time, by the way. How many understand that? It's linear time to run. But moreover, it's no worse than 3/2 n minus 2 comparisons to run precisely, not big O, but exactly. So it's optimal two different ways, in running time and in the number of comparisons, both. So it's double optimal again, just like the previous one was double optimal. All right, so we'll take a deep breath, and I will show the lower bound on this. This won't even fit in one slide. All right, so again, we're going to keep track of the knowledge gained. Yeah, question? It has linear? Oh, it has linear time and linear space, yeah, but the number of comparisons is the best possible. Yeah, so you're right. We need a little bit of extra space to, or maybe more than a little bit, to keep track of all these mins and maxes. Really, you just need extra bits to label them as mins or maxes. Or you can collect them. Yeah, how you implement it is we didn't discuss exactly how you'd implement it. You can collect these mins and maxes into arrays, make an array of greens, an array of blues, and yeah, you can do that. Or what if you didn't want to use the extra space? So now we're into the weeds of implementation. And I'm glad you said that, because even that's not obvious, because obviously we're talking about it. Right? Yeah, you can reshuffle them in the array, or even more simply than that probably, when you have a pair right here, and let's say this compares less than that, you leave them alone. If this compared less than that, flip them. Okay, so you can do it in situ, in place. So flip the pairs in such a way that the min always precedes the max after each comparison. And now when you need to find the min, just find the mean of all the odd ones and the max of all the even ones. Because all the odd ones will be the mins and all the even ones will be the maxes. So that's a good question. So yes, you can do it without extra space. But you are flipping things around. And if you want to flip it back to the original, now you have to worry about that. But it may not be necessary. That's a good question. I'm glad you asked it. How do you understand this discussion right here? Yeah, he's basically asking, how do you do this in situ, in place, without extra space? Or at least that's what I morphed his question to be. But, he was saying you may need extra space, and you have to worry about that. That's another degree of optimization. So now it's optimal 3 different ways. Because of his good question, he pointed out that now we know it's optimal 3 different ways in terms of linear time, minimum number of comparisons, and a best possible extra space. Constant, or 0 more precisely. So it's optimal not just twice, but 3 times, 3 different ways. So it's really a good day for algorithmic design here. Any other questions or comments? Very good. Yeah? Why isn't the time complexity n log n? Yeah, because you're comparing everything in pairs, so that's n over 2 comparisons. And then out of all the ones that lost the comparisons, you're just executing the previous algorithm, just going over all of them, finding the minimum the hard way from 3 slides ago. You're not executing this recursively. That's why. Once you have this list of blues and list of greens, with each list, you're just doing that from 3 slides ago. And that just takes linear comparisons in linear time. Once you have this list, you're just doing a brute force just like that. One pass. No recursion. In fact, there's no recursion anywhere here. And that's why it's not n log n or anything more than linear. Yeah. Yes, I'm proud of you for saying that. He's saying even if it was recursive, even if you were recursing this scheme on this guys, and then doing comparisons on those pairwise, and on and on and on, and building this tree here, the total time will still be linear. How many understand that? Because it'll be n over 2 plus n over 4 plus n over 8 plus n over 16, and the sum converges to 2n. Right? Very good. So either way, you'll be fine. But you don't even have to go through all that complexity of recursion, and you just make a single pass through them, and you'll know the answer. Good. I'm glad you're asking these smart questions and giving smart answers. All right. Any other thoughts or comments? All right. So we're now into the lower bound. So this is a generalization of the proof from before, except that instead of 2 categories, we're going to have 4 categories. We're going to have items that are not tested, nothing is known about them. We have items that in green that only won against other items in terms of comparisons. Everything is unique. We have items that only lost. Those are all denoted in blue. And then items that both won and lost in different comparisons against other things. So here we have only winners, here we have only losers, and here we have winners and losers, because sometimes they won, sometimes they lost at different times in different comparisons. All right, so here's the flow of elements. Now it gets a little more dicey than before. Before, everything just flowed from the first to the second. Now there's 4 things. So if you didn't test a pair of elements yet, and you just tested them, one, you can put them in the green category because they just won against something else, but didn't lose against anything else, so it goes into the green. One goes into the blue because it only lost, but didn't win. So if it only won, you know it's not the min. If it only lost, you know it's not the max. And from the first group, you can only go into the second or third group, but not the fourth right away. If you're only taking elements from the first group. If you take elements from this group and this group, if one has before won against something and now it loses against something, then it goes into the red. Okay. And if you take something that only won and compare it in something that only lost, and this still wins and this still loses, those two remain where they are. How many see what's going on? Good. It's a generalization of what we did a couple of slides ago with the simpler lower bound, because now we're doing both the min and the max. So the initial state, n things were not tested. We don't know anything about them, and nothing lost, nothing won, and nothing won and lost because nothing yet happened. The algorithm didn't run. Which algorithm? Any algorithm. Okay. And at the end, we're going to have nothing that's never been tested, because everything's got to be tested at least once. We already know that from 6 or 7 slides ago. I mean, one item has only won against other things. One item has only lost against everything. And n minus 2 items both lost and won against other things. And so this category here that only won against some stuff must be the max. And this guy that only lost against everything else must be the min. And that represents a state of knowledge in any algorithm that uses comparisons to try to find the min and the max. Right? So there will be the min and there will be the max. This isn't an algorithm. This is the encapsulation or the representation of the state of knowledge gained by any algorithm that would run to try to do this job of finding the min and the max, both. All right, so now we can start keeping track and tracking how things flow among these sets. Right? So if you have something from the unknown, I'm color coding everything. So this set here, something compared to something else, and in a test like this, means this first thing goes into the blue set, that second thing goes into the green set, because this second thing won, so it goes into the green set of things that only won. This first thing lost, so it goes into the blue set of things that only lost. So 2 things coming from the first set go into the second and third set like this, respectively. How many understand this notation? Okay. And then we keep track of all the other possibilities, right? So this guy goes to here, this guy goes to there, and that's how it flows. And by the way, if it was the opposite comparison, if this guy was greater than this guy, then it would flow slightly differently. Then the first guy would go into the green, and the second guy would go into the blue, as opposed to the other way around. So here I'm going to track comparisons, and here the negation of this comparison if you compare the other way. Okay. What if one came from the first and the second came from the second that you're comparing. They compare like this. Then the first will go into the blue. The second will remain in the green because this one came from the green. It won before, and now it won again, so it stays in the green, the second element, and so on. If it compared the other way, so if it compares the other way, if this first element was greater than that, it goes into the green. This element goes into the green. But the element that won and now lost goes into the red because it both lost and won, so it goes this way. Right? How many get that so far? Okay. So without belaboring all the points and all the cases, let's just show you all the other cases, and we're not going to waste time here going through each and every one because there's a bunch. But the point is that once you examine all the possibilities of where an element can come from and where the other element can come from, and if one is less than the other, one is greater than the other, where they started from, where they end up, you can make certain observations. And the observations is that the minimum knowledge gained, moves towards the final states. Yeah, so if two things came from the first, you get 2 bits of knowledge. In other words, you make two sets of progress or 2 points of progress. One will end up here and one will end up there. Okay? Not just one of them will move, but both of them will move out to the green and the blue if they start here in the first set. Okay? And you can similarly track how many bits of progress will be made if all these other cases happen. And sometimes it's no progress at all. And these are unnecessary comparisons. So, if both things came from the red set, both have won or lost, you already know that neither one is the min because they both each one lost and each one won in different comparisons. So neither one could be the min or the max. But nothing stops you from wanting to compare them. It's like nothing stops you from playing chess while you're adding 2 numbers together. And so the total progress of such a comparison will be 0. Okay. And that's not going to hurt the lower bound because you can make as many as you want. But things that do make progress are the ones that count, like the first one or the second one and that kind of thing. And once you make these observations, you can quantitatively say that moving from the first set to the final and red set forces passing through the 2 intermediary sets, one or the other. In other words, any element that goes from the first set to the fourth set, from the black set to the red set, has to pass through the 2 green or blue sets. There's no direct path from the black to the red using a single comparison, using 2 elements that only came from the black set, from the first set. Okay? So there's no direct, expressway from the first to the last. They have to go through the 2 intermediary ones. Okay. How many understand that? Okay, simply because if you take any 2 things from the first, you can either go to the second and the third, not the fourth immediately. Okay. Other things can get you to the fourth, but not if both came from the first. So emptying the first, remember the initial state is all of them are in this first set. And the final state of any algorithm is that set is empty. And it takes n over 2 comparisons at least to empty out the first set into the next 2. Right? And that's that second observation here that I'm making on this slide here. At least n over 2 are necessary to empty out the first set. And then emptying most of the second set takes n over 2 because at the end there'll only be 1 remaining here and 1 remaining here, and the n minus 2 will remain there, will end up in this last set because neither will be the min, neither will be the max. There's only a unique min and a unique max. Again, uniqueness here helps us because you don't have to worry about equality in other cases. So roughly n over 2 to empty the first, n over 2 to almost empty the second, n over 2 to almost empty the third. It's really n over 2 minus 1 because 1 will remain. Other moves could be made, but they're not going to make you any more useful progress. Then this is the minimum moves necessary to progress towards the final state of knowledge where 1 is the min, 1 is the max, and the other n minus 2 we know is neither the min, neither the max. Yeah.
So you sets
Yeah.
are like a core part of the algorithm, but you counted moving it into the red set as no knowledge gained. I mean, maybe that's not important, but what's the intuition behind, like, you said when you move something from the green or the blue set into the red set, you counted it as zero knowledge gained, but like, that's
Oh,
not the point.
well, it's not zero knowledge. When you say emptying emptying the green or emptying the blue, whenever something moves out of the green or out of the blue, it can only end up in the red. The red is where they're going, where they're being emptied into.
But isn't that like you're gaining some knowledge that that one is not the min or the max?
Yeah,
So it's
yeah, and I'm counting it here by having it leave the green. So I'm counting that as a step. When it exits the green, that's a bit of knowledge gain. Yeah, and when it exits the blue, bit of knowledge gain. But to answer your point, where are they going when they're leaving the green or the red? They're going into the green or the blue. They're going into the red by leaving the green. There's only one path from the green and one path out of the blue, and they both point towards the red. So when I say leave the green, they're going to the red, and I'm counting that. So I am counting those red-involved motions or movements of elements. But I'm counting them here and here. You know, yeah.
On the third and fourth bullets, the word most is used. So is most all but one?
Yes. When I say most, I mean all but one. Okay, that's important. So the motion is pairs from here will end up both in the green and the blue, both places. So a pair from the first set will end up in the second and third. And then eventually, not necessarily right now, but eventually, both of those will migrate to the red, to that last set. That can happen, at some point in the execution. But the algorithm is not going to finish until all that happens. Because at the end, only one thing must be identified as the min, one thing must be identified as the max, and these are these two middle sets. And the rest are either implicitly or explicitly known to be not the min and not the max, and only then can the algorithm terminate with the correct answer. Which algorithm? Any algorithm. Now you're getting it. How many are sort of seeing what's going on? Not necessarily everything, but are kind of grokking the gist of this. Where does the word grok come from, by the way? What does that mean? See if you have a classical literary education, which we hope you do here at the UVA. That's what we aim to give you. Anyway, extra credit. What's the word grok? Which famous novel it comes from? I'll give you a hint. It's science fiction. Okay, so any other moves will not get you the final state any faster. For example, you can take two things from the red, compare them, and then they'll all obviously both still remain in the red, but nothing stops you from doing that. But that's not going to get you any faster to an answer or a solution when you run an algorithm, any algorithm. All right, so the total number of comparisons required to get you from an initial state to a final state, no matter what algorithm is running, is the sum total of these three quantities, which is 3n over 2 minus 2. And amazingly enough, that algorithm from a couple of slides ago did meet that necessary lower bound with an upper bound by virtue of being a correct algorithm. So that algorithm is optimal in the number of comparisons. Not asymptotically, but exactly. Of course, if it's optimal exactly, it's also optimal asymptotically. If it's optimal asymptotically, it's not necessarily optimal exactly. So for example, with sorting, we know that n log n are necessary. That's the lower bound for sorting. But we don't know what it is exactly. Maybe it's 2n log n. Maybe it's 3n log n. We have some more precise characterizations, but the real answer of exactly how many are necessary in the absolutely minimum, actually, nobody knows. It's an open problem still after almost a century of examining sorting in great detail and depth. Here, we're giving the exact answers, not just the asymptotics. Yeah.
Is there a name for this proof technique of making a state machine of knowledge known?
He's asking, is there a name for this proof technique of having a state machine? So it's not quite a state machine in the sense of finite automata, but it is kind of a tracking of states of knowledge, yes. So first of all, it's a lower bound proof. it's also a proof by contradiction. Any lower bound proof is kind of assume there was an algorithm that did this faster, then this shows you that it can't be done any faster. So it's an implicit proof by contradiction here. So generally it's a lower bound proof. Secondly, it's a proof by contradiction. And you can call it proof by tracking the state of knowledge in the execution of any algorithm. I don't know there's a special name that does describe it more succinctly than that. But yeah, but it is a proof by contradiction. It is a non-existence proof. That's another way to say this. This proof is a non-existence proof. Why? What does not exist that this proves that it doesn't exist? This is a proof that we're not a millionaire. Something doesn't exist. What doesn't exist? Why is this a non-existence proof?
An algorithm or a way of reaching the final state.
Yes. It shows that no algorithm exists that can find the min and the max faster than that in terms of number of comparisons, the exact number of comparisons. So it's a non-existence proof. So yeah, that's a name for it. But it's a bit subtle why it's even a non-existence proof. You have to keep it in mind, all these logical relationships of what we're doing here. This is subtle, I agree. It's not obvious. And if somebody asks you to prove a lower bound like this, I mean, you know, if you would have come up with this argument with the four buckets and how knowledge moves around and all these arguments and all these special cases that we saw on the previous slide and tracking it, we'll all be very impressed. Probably give you a PhD on the spot if you can, you know, come up with this. You know, the people who first came up with these probably did get PhDs for that. Nowadays, you know, it's half of a lecture in an algorithms course, but you know, 40 or 50 years ago, it was a PhD. This kind of subtle insight and kind of crisp, you know, wrapping of a mind around this kind of notions and lower bounds and non-existence proof across any one of an infinite number of algorithms that can do the job. And that's pretty impressive. It's not trivial. Any more questions or comments about this? So again, lower bound proofs are not easy. And now this is the hardest proof we've seen so far in this course, and that's not the hardest we will see. But so far, this was the least trivial thing we've seen so far in terms of a proof. All right, so given n integers, find the maximum and the next to the maximum. Remember, we gave this problem as extra credit. How many solved this? How many worked on this, which is really the important part. Okay, and the rest, don't care. That's all right. Have fun programming device drivers for IBM for the rest of your life. That's okay. You'll still make six figures, but Google will not be impressed with you if you don't try solving problems. Because during your interview, they'll give you problems and they'll watch you trying to solve them. And if you just passively just wait for answers all throughout, you know, you can't cram over a weekend for becoming a MacGyver. I mean, I'm just stating the obvious. Or Matt Damien on Mars. You know, it doesn't come from a weekend of cramming. Trust me on that. Okay, but find the max and next to max. There's very easy ways of doing it. If you want to find the max and next to the max, one easy way of doing it is first find the max, then take that away from the set, and then find the max again in the remaining elements. And now you have the max and next to max. How many get that? That's an algorithm. How many comparisons is that total? Find the max, then take that away, and find the max on the remaining elements. Now you got both. 2n minus 3, correct. How many see that? 2n minus 3. Okay, good. Obviously, that's not the best we can do. Otherwise, we wouldn't be here bothering you with this problem some more. Right? So we're going to do better. Instead of 2n minus 3, we're going to show you can do it in n minus 2 plus log n. So we're going to do it using a tournament argument. Right? Let's say you're playing tennis, and you play tennis, and you play in pairs, and then the winners of those pairwise tennis matches play each other, and eventually at the end, one victor comes out victorious across the entire set. So you play in pairs. You take the max of pairs. And then you take the max of those maxes, right? And the tournament proceeds, and eventually in the quarterfinals, semifinals, final, and the finals. And at the end, there's one winner overall. That's the best player, among the entire set. And there it is. And so we're doing that recursively, what we said earlier. Keep finding the max of the maxes. And that's how a tournament works, right? It doesn't have to be tennis. It could be any sport, obviously. Football, could be any sport, the Olympics, swimming, or whatever. Okay, so the total number of comparisons here is n minus 1. How many can see that? Because what you said earlier, the tree, converges to a linear amount. N over 2 plus n over 4 plus n, and so on, converges to n minus 1. Okay, so now I'm going to present this tree kind of diagrammatically as this triangle representing this whole tree. And let's say that somewhere in the bottom, again, they're all unique, so we don't have to worry about equality or ties. Everything is unique. So there's always winners and losers, never ties. So the next to the maximum must have started somewhere at the bottom of the tree, just like everything else started at the bottom of the tree and tried to rise its way to the top. Okay. So the next to the maximum, if you have a bunch of players in, say, tennis, the second best player in the world, there's only one player that second best player could have lost to. Because if they're second best, they're going to win against everybody except the world champion. Right? How do you get that? Obviously, they're all unique. So the second to maximum, the second to best player started at the bottom and made its way, or at least tried to make its way to the top, and at some point was thwarted and didn't get to the top because the winner, the overall champion, went to the top. And the overall champion is the only player that could have beat this guy. So in the final tree, where will this guy end up as they keep playing and playing and playing until there's one winner emerging?
It's one of the ones that the winner won against.
Yeah. It's not right next to the root. How many can see that? It's not right next to the root. Why? Why isn't it like right there, right next to the root? Yeah, this guy could have been eliminated right off the bat by chance by playing the true champion and would have lost right on the first tournament. Never mind 3 or 4 iterations later. They could have lost right away. Because the true champions were right next to them, playing them on the very first round. And they would never get any higher than the first level. That wouldn't make for great television drama. Ideally, you want so when they actually pair up players in the actual tournament, whether it's tennis or fencing or whatever Olympic sport or sport you want, they don't pit the best players against each other right away. Why? Because they will be eliminated. Most of the best players will be eliminated right away, and for the rest of the tournament, all you'll see is mediocre players, and the champion. So it wouldn't be very interesting. So you want to kind of mix and match them, so that the best players will survive, and then eliminate each other. And towards the end, you'll have only good players, and then those will be eliminated. And finally, one champion will barely beat the next guy that's second best, and then that makes for very nice drama and television and reporting and excitement and fun to watch, right? And movies are that way too, right? When you have a movie like John Wick, or there's all these firefights and whatever, you don't want you want the two really good people, usually the good guy and the bad guy, to last to the very end. You don't want John Wick to eliminate the arch enemy that's almost as good as him, like in the first 2 minutes of the movie, and for the rest of the movie, he's just beating everybody else up, mopping the floor with them, without any effort. That's not very good entertainment, right? So think about it. But anyway, the point is, this guy could have been eliminated right away, but he could have been eliminated as the winner rose up. The second to next winner would have been beaten by the winner on the path the winner took to the top, and it could have been any one of those on the path to the top, the second to best player. It doesn't have to be way at the bottom, it doesn't have to be way at the top, it could be anywhere near that path, but how long is this path? Because this is a binary tree, because they're pairwise. So how long is this path if there's n players? Log n. Question?
Okay, so this
if I take 6 players, then I'll have 6 comparisons to get the first maximum number.
Well, so there's n players, so the first level will have n over 2 comparisons.
Let's just take 6 players. Why even bother ourselves with n players? Let's just say 6 players.
Well, let's make it a power of 2, so it works out more nicely. Yeah, so make it a power of 2, and then if it's not a power of 2, you can pad it out, to make it the next power of 2, and then you'll get very similar result. But let's not worry about these kind of cases right now. Let's make sure it's a power of 2. So when you say log, the answer is a whole number, because it's log base 2.
Yeah, for this case, because I was talking about 6.
Oh, okay. So make it 8. Yeah, good point. So that's right, and that's a good insight. But I would say make it 8. See, it works with 8 or 16 or 32. And then if it's not a power of 2, add a few more that are non-players. That would lose to anybody. So they're just padding out the crowd to make it the next power of 2, and then it would be these numbers. Okay, good point. Any other thoughts or questions? All right, so first you do n minus 1 comparison, and then you compare all these log n to each other the hard way using the naive algorithm from 10 slides ago. And that's log n minus 1 comparisons, just straightforwardly comparing them all, finding the maximum of all of those other than the true champion. And so the sum total is n minus 2 plus log n total are necessary for finding the maximum and x to maximum. So this proof is an algorithm. So that's sufficient. It turns out separately that it's also necessary. We haven't proved that it's necessary. We showed that it's efficient by giving the algorithm. The algorithm is right there. Of course, if you had to write it in pseudocode or code it up, you can convert this to an algorithm pretty straightforwardly. How many can see how converting it to code will work pretty straightforwardly? Not a big deal. But the idea is not the code. The idea is that the champion could have only beaten the next best from the champion can only have been lost to the champion. There's only log n possibilities there in this tournament style elimination, and that's how you'd find it very quickly without too many comparisons. Now the naive method that we just said find the max in the previous slide, the naive method finding the max and next to max is find the max, eliminate it, then from the remaining one find the next to max, again using this brute force naive linear scan, and that was 2n minus 3. This is n minus 2 plus log n, so it's almost twice as good, factor of almost 2, better than 2n. So it's quite a bit of savings here, not just a quarter, but almost 50% savings. Because log n is much, much smaller than n. Now separately, you can prove, or it has been proven, that n minus 2 plus log n are also necessary, not just sufficient. In other words, it's also a lower bound, the exact lower bound on any algorithm finds the max and next to max. That's not easy to prove, and we won't do it here. But for extra credit, try to prove that too. Okay, any question? Yeah.
Yeah, just a question. There's the number of comparisons that we are trying to find out. We are trying to find out when we're using comparison to find the maximum minimum, right?
Yeah, we're using comparisons, so we're counting comparisons. So either two things is one less than the other, one bigger than the other. And we don't have to worry about equality because everything is unique without loss of generality. You can break ties based on the indices, the array where these items came from. Okay, any other thoughts or questions? Because now we're going to go deeper into selection. So what we've been doing so far is selection today. We selected the largest, the smallest, the largest and the smallest, the largest and the next to largest. Right? These are called order statistics, statistics about order. Largest, smallest, next to largest, third largest. Now we're going to go full out and find the ith largest for any I. So this generalizes everything we've done up to now today. We're going to find the ith largest for any I. And now things will get even more esoteric. Okay, so first we observed that finding the ith largest can be done by successive application of finding the median. The median is the n over 2 largest. It's the one in the middle, right? Assuming n is odd in this case. So the one in the middle is very specific, very unique, because they're all different from one another. They're all unique. How do you reduce finding the ith largest to just repeatedly finding the median? Okay. Not that hard to see. Let's say you have 100 things and you want to find the ith largest. The median is the middle one, assuming it's, the median is right there. Assuming there's an odd number of them, the median is one of those. Or, in particular, the median of an even number of things is maybe the average of the middle two, or either one of the middle two. Anyway, any way to define it, it's all equivalent. So if you want to find the 87th largest, say, in a group of 100 things, and you know what the median is, all you got to do is take everything larger than the median, and among those, find the 37th largest, because 37 plus 50 is 87, or 87 minus 37 is 50, and 50 is the median. So if you want to find the 87th largest of a group of 100, it suffices to find the 37th largest in the upper group of 50 of those. All the 50 that are larger than the median. How many get that? Yeah, that's pretty straightforward, right? And now you still want to find the 37th largest in this group of 50. So what do you do now? One word. Recurse, or iterate. They're really equivalent if you think about it. The compiler always converts recursion into iteration. How many understand that? So you say recursive for the compiler, for the machine, for the hardware, it doesn't really mean recursive. It means iterative. But anyway, and now you want to find the median of this group of 50 and see how this item 37th compares to the median. The median will be the 25th element of this 50. So it's 25, and now you'll find the 37 minus 25, which is 12. You'll want to find the 12th item in the upper group of these 25. How many get that? And you just keep going. How many calls to the median did you do overall? How many repeated calls to the median subroutine did you do overall to find this ith largest? Logarithmic number. How many see that? Because the space is divided by a factor of 2 every time. It's half as large each iteration. So before you know it, you only have one thing, and there's your answer. And if the median subroutine worked in linear time, we're not saying how, because that's a huge, tricky question to begin with, and we'll do that, but we'll do that next time. If the median subroutine worked in linear time and you made logarithmic number of calls to it with smaller and smaller inputs, what's the total amount of time you're expending as a function of n? Big O of n. How many can see that? Because first you call it an n things. That's linear in n. Then you call it n over 2 things. Because we want to find the median of the upper 50. And then you call it n over 4 things. So the total time is linear in n, then plus linear in n over 2, plus linear in n over 4, which is just plus n over 4, plus n over 2, back to linear. The total will be 2n, right? How many see this thing converges to linear? So you make logarithmic number of calls to the median subroutine with smaller and smaller by half inputs, and the total total time expended in total will still be linear. Which means if we have a linear time algorithm for the median, this scheme, this set of observations, gives us a linear time algorithm for any ith largest for any I, not just for I is equal to n over 2, which is the median, but for any arbitrary I. That will work in linear time too. How many see that? So you can do ith selection in linear time, assuming you can do ith selection for the median. So now it all depends on being able to do ith selection in linear time for the median, which is what we'll do next time. But that's why we're after the median in linear time now, because that'll give us any ith selection in median time as well. So solving the median is as general as solving the arbitrary ith smallest or ith largest, not just I is equal to n over 2, which is the median. So we reduce the problem of finding the ith largest in the same time, linear, to the problem of finding the median. But it's got to be worst case linear time, not average case. And next time, we'll do that. Maybe in the interest of stopping on time, we'll stop here. Any questions about any of this? How many are working in groups? Good. The rest of you do that too. How was the pizza on Monday? It's good? How many were there on Monday, out of curiosity? A bunch of you. Okay, that's good. A couple of dozen. All right. All right. See you next time. Thank you.
Had a question about the submissions.
Mhm.
So we have to submit two NPV answer, and almost at the end of submission the required readings, except the books, and the books will probably take more than a week to finish, like one book. So if we do not submit the coming week, is that okay, or we have to balance?
Well, you should still submit two, two per week. They don't have to be books, so you can do the TED talks or the easy stuff if you're pressed for time, and you can submit the books later on. But you should submit the books as you go, not all in the last 2 weeks,
Oh yes, I've
obviously.
started, but it's just
Yeah,
taking time.
but you still need to submit a couple of things per week.
Okay. And do extra credit problems count in that submission? Actually,
No,
you have to
those are
do,
separate,
right?
separate
And
tracks.
do they also have a per day limit submission, like extra
For the
credit?
extra credit, yeah, yeah. What I don't want is people to submit 50 extra credits on one day. Obviously,
So
that's
like two or three
two per. Let's say two per day.
Okay, so I can have two submissions, like reading separate plus two extra
Yes,
credit
yeah.
problems.
And the reason for that, I want to pace it so that people don't pull an all-nighter and towards the end of the semester and submit 20 or 30 extra credits in one day, which is
I
not even
just
credible.
submitted
Yeah.
like three problems and plus two readings one day, so I
That's
just
okay. Two or three, we prefer to be two, but you're still respecting the spirit of this rule, which means not big cramming sessions towards the end of the semester. Yeah, so that's fine. So you're nowhere near this crazy scenario where somebody submits 50 things in one day and expects us to believe that they did this in 1 or 2 days. That's not credible. So that's okay. But that's the spirit of this rule is to reduce the amount of like crazy cramming that some people have done in the past. So, all right, yeah.
So there's a term projects for the class, or
Yeah, there's a project, and the project, you can come up with something interesting and run it by me, and I'll say it's okay, or I'll say it's too difficult, or maybe it's too easy. And you can work in groups of two, not groups of 17, obviously.
would
'Cause,
3 be okay?
I'd rather it be two, unless you're doing something really ambitious that requires 3 people. Like, what did you have in mind?
We don't have much in mind. We're undergrads, so
Yeah, it's okay.
yeah, but yeah, we don't have projects in mind. Do you have like examples?
There's an example on the website, the puzzle solving problem. It's posted on the class website. So you can look at that, and that gives you a good gauge of the level of difficulty and what it entails. But people should either work in groups of 1 or 2. 3 is probably too much. Unless, I don't want to completely exclude that possibility, but you tell me what you want to do, and you justify to me why it takes 3 people, not 1 or 2.
Okay.
Yeah,
Um,
that's all.
What are the approximate deadlines for when this project?
The project is due like maybe the last week of the semester, like right at the end of classes, basically.
Are we going to talk about it at all in class, or is it just something we do?
If you ask me during class, I will talk about it. And I mentioned it during the first day, but maybe it's been too long. But if you ask me during class, I'll say more about it. But it's some programming of some algorithms, and there's a lot of leeway in what you can do and what you choose to do. So there's some interesting algorithmic stuff that you always wanted to do and didn't have an opportunity, and now you get credit for doing that. And, be my guest.
How graded that?
What did I say, about 30%? Yeah, on the first few slides, there's the percentages, and I think I said 30% for the project. So it's a big chunk of the grade. But if you start on early, it's pretty easy to finish, right? I mean, if you save it till the last weekend, it won't be easy to finish. So don't do that. obviously.
Okay, we'll come talk to you.
All right. So let me know what you want to do.
Thanks.
All right.